Hi, Bob. Test.
Good morning.
Good morning, Bob. I just wanted to make sure you were there. I'm going to place you back on mute shortly.
Very good.
Okay, Bob Fall, the floor is yours.
Okay. Good morning. Welcome everyone to the fourth annual presentation by Professor Kimmerling on grand challenges and key needs in integrated photonics. Each year he's presented an update to this report based on the most recent edition of the IPSR roadmap. And we have seen that during this period, a number of gaps and needs have been identified during the 4 years, but some of them have not yet been closed. I would point out, please listen carefully to the gaps that he describes, because some of them, their closure is delaying the introduction of integrated photonics into high volume, low cost manufacturing. And this lack of closure remains a great challenge. So without further ado, I turn it over to Professor Kimmerling to give you the 2019 list of grand challenges and key needs in integrated photonics.
Thanks, Bob. This has been a critical year for photonic integration. The ramp has steepened significantly. The insight into where the future is has become clearer, and it's my job to do my best at giving you both the high-level insights that we've obtained during the year, as well as some deep dives into the new technology. Okay, we'll look at what we think is going to be important in the next year and put it in the context of 3 applications: Datacom, RF, and sensing, where RF is looking like it may be a common platform for LiDAR, 5G, and a number of other applications. And overlaying on all of that is the constraint of meeting cost, energy density, and bandwidth density. So when we think of the value of a roadmap, we'd like to find one vector that we can all use to guide us in making our decisions, and it's looking more and more like if you choose the vector of density for photonic integration, you're going to be able to reduce cost, reduce power dissipation, and increase your bandwidth density. So keep in mind, density in general may be the scaling vector. So critical themes for 2019, very important is ASIC co-packaging. We'll talk a little about that. Optical connectors, if you're going to realize the benefits of photonic integration, you have to spread the signal through the system through connectors, and we'll look at the constraints on connectors and the issue of scaling density while we're doing all of that. So we'll look at 3 technology application areas, as I mentioned earlier. We'll take a quick look at economics and how the value of time to money is important, and what is missing and what needs to be done in order to achieve that, and the issue of supply chain coordination, because we don't really have a supply chain from end to end for integrated photonics. And lastly, the big success theme, I think, is keeping your eye on the endpoint, which is electronic-photonic integration. Electronics is looking for solutions for both reach and bandwidth density, and photonics offers those solutions, and it's a matter of how photonics can integrate itself into electronic systems rather than the reverse. So if you look at the efforts in defining a scaling vector for electronics, it's more or less uncoordinated at this point. You can't go any further in scaling clock frequency, transistor count, and so forth. So the idea is, well, maybe we can just scale the functionality of a package by stacking chips and making packages much more functional, which is a large technology challenge, and one that we meet with photonics, because integrating photonics and electronics at this point is primarily a packaging challenge. The more than more is looking at more or less anything goes, nanotechnology, quantum computing. Maybe photons are good, but they're just as weird as all the other things if you're an electronic designer. And then lastly, the path for integrated photonics, which is architecture are getting parallel, so they're becoming more communication-centric, and you have to figure out from the very top down how to integrate photonics in a most cost-effective and performance-effective way. So for any of those who are still asking a question, is it really happening or not? This is some data that I just pulled out of the roadmap integration that's occurring between the European roadmap and the IPSR, Integrated Photonic System roadmap that we maintain here at MIT with AIM. And so the commercial ramp has expected to be strong because photonics is needed. Back in the early days, Luxtera and Quatura, the first to market. Luxtera is a strong player right now. Quatura is reforming. Intel Silicon Photonics transceiver is now being used in hyperscale data centers with a number of customers listed here. There are system vendors, Juniper, Dell, NTT, and so forth, who are using silicon photonics in their systems. Chip manufacturers and supply chain has been already committed to developing products, and some are listed there. Offering and Global Foundries, ST Micro, TSMC, and TowerJazz run products with standard PDKs. And there are a number of R&D laboratories, including AIM, CE-LEDI, IMEC, and so forth, that are running PDKs for silicon photonics as well as integrated indium phosphide photonics. So the idea of integrating a design infrastructure based on automated design software has been truly disruptive to the fab. Now one can guarantee that at least the design itself is consistent with layout verification and design rule checks for the various fab layers and implantation doping. And from now on, it's critical that process capability and test are integrated into the fab itself, so that the critical path to on-time product, which is that time to money issue, is achieved. So we'll look at the end at what the foundry model looks like and where it's going, and how we would evaluate its potential for the future. One thing that is good for an overview is a a grand challenge study that's being done at the MIT Microphotonics Center, which is looking at electronic-photonic interconnection and how it's going to proceed between now and 2035. So as you know now, there's a standard 7-level interconnection hierarchy, but the drive for greater and greater connectivity in parallel systems and flatter architectures is almost surely going to modify that 7-level interconnection hierarchy and the need not to have new protocols every time you jump from one level to the other if you're using photonic seamless flow through the system. It's expected to make changes. So there's a study looking at that, and I'll give you a couple of the early insights. There's a interim report that's being posted on the website. If you need anything that haven't already given you website URLs for, just write us and we'll let you know. So this is generally the trend. It's really not something in its high level that one can really question. Miniaturization, disaggregation is important, and I'll talk a little bit about that from an economic point of view. System and package is very important once photonics gets inside the package, and then system on chip eventually. So if we look at this sequencing, the top level is primarily pluggable, where density has not really hit the crunch as far as putting things together. But once we use embedded transceivers on the board, then density begins to hit the limit. So we need to solve a way of doing surface mount of transceivers on the board, a way of dealing with the flyover fiber clutter and how that is going to impact the current issues of airflow as well as density inside the rack. And then eventually, and I'll give you some more detail about the transceiver chiplets and package with a slide from Intel, looking at how do we handle the various protocols as well as the need to get bandwidth as close as we can to the processor. And then finally, at the end of the line is everything's monolithic and photons are flowing throughout the system. So typically, if we look at the schedule, optics on board was initiated commercially in 2016, and we're looking into the future where the data center switch is working at 51.2 terabits per second in 2023, and certainly we need to have the photonics in the package at that point. We'll begin with optics and package around 2020 with the transceiver chiplets or tiles, if you like. They're in the roadmap of most of the major transceiver manufacturers. And on top of that is the issue of what are going to be the communication protocols, and will there be differences in the implementation of the packaging as far as through silicon vias and so forth, depending on whether you're working with an FPGA or you're working simply to take a switch signal out. And then lastly, optics on chip, beginning to emerge around 2025, where you'll be implementing optical signal processing. And the advantage of doing that is that you can do a lot of that passively without power dissipation. One of the big questions that we'll look at, and it's certainly a roadmap issue with the monolithic integration twig, is what happens to the laser during these transitions. Is it going to be moving closer to the chip, or is it going to be moving further away? And as you'll see, there are answers to both of those questions. Well, here's a slide that was presented last week at the Roadmap Conference here at MIT by Intel, giving their vision for photonic integration. Today, and if we're just looking at the Ethernet switch and the ability to communicate that switching bandwidth to the rest of the system, Right now, it's involving optics which are pluggable at the faceplate. And so that presumes that the bandwidth from the switch to the board faceplate is capable of being carried by copper traces. The next step is to put onboard transceivers, which are the embedded transceivers that I mentioned to before, that can then carry the higher bandwidth from the Ethernet switch to the faceplate and then into the system. And one of the big issues there is we don't want to put pluggable optics at the faceplate again because there's too much power dissipation and it takes up too much room. So we hit a density limitation. So what we'd like to do is once we create the photonic carrier, take those right through the faceplate with MP connectors and into the system. And there's a lot of questions as to both what connectors are we going to be using at the transceiver that's embedded on the board, and what connectors are we going to be using throughout the system as we carry the optical signal forward. And then as the data rate gets higher into the tens of terabits, then the full integration of transceivers into the package, the switch package, is envisioned. And as you see here, we've got all these yellow tiles are optical transceivers which are carrying the signal away from the switch core. And then one has to think about what is going to be the architecture for the optical carrier from that package outward. So Intel envisions hundreds of fiber connections per edge. Most of the vision for the future is that edge connection is going to be the one which is most consistent with electrical connections to the processors and edge connections for I/O for the fiber. But it's a big question is how do we get the optical density, and that's going to be putting pressure on WDM interfaces, and how are we going to be able to incorporate WDM into a hostile environment with regard to temperature variations as well as high bandwidth density requirements. Okay, so if we look at electronic-photonic interconnection in the way it looked this year in 2018, the copper technologies were well advanced and they have a good supply chain to support them. The onboard solution is necessary, and you need a planar single-mode waveguide technology. And as I mentioned, there are big issues as to how we'll be able to implement that. The surface mount technology is now being implemented with transceivers, and so I think that's beginning to be a solved problem. Once we realize that pluggable is not a solution for board level mounting, it's only a solution at the faceplate. So then we'll look at that picture that we showed earlier. The conventional motherboard solution is okay, but as we build more and more photonics into the modules, then we need to think about design from the processor chip through the photonics in the module into the interconnection hierarchy and then into the system itself. So that supply chain, which is going to solve those problems, is really critical. If you think about how copper was introduced into electronics technology, originally copper was feared to be a killer for silicon electronics chips. In fact, it was called deathnium in the early stages because copper precipitates always took away from the performance of the chip. However, through diffusion barriers and chemomechanical polishing and low-K dielectrics, all of these things which were actually developed in the supply chain, not in the chip manufacturer's technology, came into play, and copper was able to be used for multi-level interconnects on the chip. Now we're thinking about where is that supply chain? Do we have to have a vertically integrated company to do that, or with the volumes of manufacturing that we have now, can we evolve a supply chain working independent of one another? So one of the advantages of a roadmap, and the reason I'll encourage you to get more involved in that, is that we begin to see where there are common needs in a supply chain, and we can develop suppliers and vendors that are able to supply those technologies because they know that there'll be more than a single customized market to meet with those solutions. So let's think about the challenge of moving photonics from I/O ports on the faceplate into the system. So the first thing you realize is that the packaging and connectorizations are the big issues. We can make transceiver chips, but if we can't solve those issues, then we don't really have a system architecture. So the best solution to that is single mode. Silicon photonics is consistent with that single mode because you can envision scaling the data rates through the combination of a DC light source and a modulator. And then with the modulator, you can scale both the on-off keying as well as several other advanced modulation formats into getting 8, 16 bits per hertz spectral efficiency. But in order to implement that, you need good single mode connectors that can be implemented at low cost. And one of the ways to implement that is with the expanded beam connectors, where you take a typical 10-micron core from a fiber and expand it to 80 microns, and you relieve the alignment and dust limitations that you have with connectors in general, and then apply it to single mode technology. And these expanded beam connectors may be even an early entry point for multi-mode at very short reach, particularly for automotive applications and applications of that kind. So we're looking for high volume places where you'll begin to see solutions to the connector problem and ways to alleviate the performance degradation and cost of alignment that they have presented in the past. So an AIG is an application interest group that is a spinoff from the roadmap. And this is a group of companies that are interested in identifying the system requirements and the technology gaps and working together to bridge those technology gaps in order to create the supply chain necessary to feed the system solution. So this is one on onboard optical interconnection. It started 2 years ago, and it finished phase 1 and looked at the system and arrived at the idea that surface mount is necessarily going to be the implementation rather than pluggable, and it was able to demonstrate a 0.2 dB single mode connector loss for signals going through the system routing through a daisy chain of at least 8 connectors. And so this is the beginning of understanding how to do low-cost, high-efficiency connectors. Phase 2 is now looking at taking that connector to the package level. There is no onboard solution to embedded waveguides, so for the near term it will be flyover fiber, and the solution to that will be dictated by how we get a connector from the package into the flyover fiber. And the team is now looking in their phase 2 at implementing a expanded beam connector from the package to the flyover fiber assembly. And anyone interested in engaging in that. They have about 12 companies involved in it now. The criterion for engaging in a study of this kind is you need to envision yourself as supplying one of the options for a solution in the supply chain for implementing a prototype. And if you can do that, then you get accepted into the team and the prototyping begins. For the expanded beam, just one final look at why that was chosen as the preferred solution. The advantages are relaxed alignment, greater tolerance to debris, low mating force, which is very important for connectors, and potential lower costs because of the fact that you don't have the maintenance as well as the precision required in manufacturing. The concerns that they're looking at and they want to obviate by the prototyping is, will they need anti-reflection coating to reduce the loss even further? Angular alignment is important when you go to expanded beam. Lateral alignment is usually considered a almost solved problem, but if angular alignment is not solved, it's going to be important to understand and to develop a solution. And then lastly, the tolerances for the fiber connector. Fiber ribbons are envisioned. You need molded optics and a fiber holder that are going to be holding all of the optics in place over a number of different thermal and vibrational conditions. So if you want to join an application interest group, there are 4 of them that are in the startup phase. The 3 phases are define the system requirements, define the gaps, and prototype and test solutions. So Datacom, LiDAR, analog RF, and sensing all have chosen what their targets are going to be, and the one for onboard is being administratively supported by INEMI at this point. So again, any questions about that, just send us an inquiry. So that's looking at the board. Let's look at the package, and we already looked at the challenge in the package is, first of all, to foresee the time when transceivers are inside the package rather than an independent entity on their own. And then we might look into the future, what happens when light is just flowing through the system in general? What is going to be the position of the light source? So let's call this laser integration. We asked this question last week at the roadmap meeting here at MIT, and the graph on the right is sort of a put together of the solutions that were presented at that meeting. And the picture on the left is a presentation that was presented at that meeting 2 years earlier by a data center architect from AIST, Ishii-san, where the light source is in a rack. And so you get a highly regulated light source. You can generate frequency combs or whatever you want to, but it's all controlled in the rack. And then they're distributed to the server racks and throughout the system from a central source. And you can argue the advantages of that and the fact that the laser is a special device, and it has traditionally required good heat sinking, hermetic sealing, and relief from drift of the wavelength and so forth. So that is one potential solution in the offing. But if you look at what we're doing now, Intel, NTT, and Ghent University presented on integrating lasers by bonding, and by coupons. A big issue in putting lasers on a 300 millimeter wafer is the efficiency of use of the indium phosphide materials, which are one of the more costly aspects of laser processing. Next is laser on interposer. MACOM, AIO Core, which is a startup from the Petra project and team in Japan and AIM all have interposer offerings for laser integration. Luxterra in its presentation has showed that their future architecture for board level integration is going to be a separate optical power supply, not integrated into the transceiver as their laser currently is in that package. And then lastly, the centralized optical power supplies you see here. So all solutions are on the table now, and there's going to be a lot of thinking about where we need to invest our R&D in order to realize what the endpoint for laser integration will be. This is the way the roadmap is approaching it. And this is a plot that was put together by Abdul Rahim from the University of Ghent, looking at the various ways of chip-level integration of compound semiconductors with the silicon photonics, and what the specifications are that we're going to be grading and predicting as to how they will move through the various timelines that the roadmap has established. So process complexity, heat sinking, integration density, as I mentioned, 3.5 usage, material usage efficiency, wafer scale integration, all of the packaging is moving in that direction. Laser integration process throughput, how long does it take to do the laser integration step? The ability to qualify laser parts before they're put in there, and then what is the technology readiness level maturity. And so all of those will be mapped out for the different ways of doing it. Flip chip integration for interposers, the pattern direct epitaxy, the transfer process, as well as the indium phosphide moving into the foundry. So if you look at the big picture, the feeling is that hybrid always precedes monolithic, that when technology nodes such as electronics and photonics advance at different rates, one has to be able to accommodate that at the same time, and that when you're packaging things together, you need to co-design the chips and the package together, and you need to be concerned with the assembly yield penalty because that's going to affect the cost scaling. So monolithic may be the ultimate solution, but the interim decisions are going to be made. What are the cost, design, and performance benefits, and how do we meet the challenges of density, connectivity, and packaging? So the thinking is the near-term compromise will be that as far as electronic photonic integration in the foundry, it may only happen for node insensitive functions, such as a stability control system for a universal WDM interface. You might want to use thermal heaters and so forth in order to keep that interface stable. It certainly would be compatible with a stable laser source on the outside, and even on the inside, it would be able to migrate with drift and laser wavelength with temperature. But that doesn't require a lot of advanced technology as far as the transistor nodes themselves, and it does alleviate a lot of interconnection complexity that would happen if you had to do that from a chip on the outside. Okay, let's look at the chip. I have just a few things that are considered real advances in the recent year as far as the monolithic integration. One is the isolator, 40 dB isolation with 3 dB insertion loss. And this is a resonant isolator, which is the smallest footprint isolator that can be put in a silicon photonic circuit. And essentially is a resonator which is coupled into the optical bus. And if you put a magneto-optical material on one side of that resonator, then the group velocity and hence the resonant frequency, it becomes dependent on the direction of propagation of the optical signal. So one can pass one signal and reject the other signal with an isolator of this kind. And a loose diagram of how you measure insertion loss, isolation ratio, and operating wavelength is given on the right, and the next slide will actually give you the recent data. But what has been demonstrated, and it really tells you once you get the processing part solved, then you can begin to make trade-offs as to what your system needs. So if you can do a mode conversion, then TM ring resonator can afford that 40 dB isolation with 3 dB loss. If you use the same structure for TE, you get 20 dB isolation and a higher loss. If you go to Mach-Zehnder version of this device, in order to get a wider bandwidth, you can get 20 dB isolation over a 2 nanometer bandwidth, 30 dB peak isolation with a 6 dB insertion loss, and TE slightly degraded behavior over that. The way this is achieved is actually moving away from the original design where the magneto-optic material is placed on top of the waveguide and placing it under the waveguide as shown in the cartoon in the middle. And then using a grayscale lithography in order to taper the amount of optical signal that is flowing through the magneto-optical material. And the data that you see on the left is actually measured data for these devices. And what you can see is that if you're able to tolerate an arbitrarily narrow channel, then you can always trade the insertion loss and isolation against the channel width. If you want to get the channel width larger, then in order to accommodate, let's say, for instance, laser drift in wavelength, then you have to give away a little bit as far as the insertion loss. So this is beginning to make us think about how stable do we want our laser power supply? Do we want to trade away the isolation in order to allow for laser drift and so forth? And eventually we'll make those decisions, but it's beginning to open the door to how we see these trade-offs emerging in the future. An interesting application is video, and I put this in here because video actually is the driver for I guess what I would call internet capacity, but video is a huge challenge that's also driving 5G as well. So if we think about the ultimate goal, and it's actually one of the possible metrics that we might consider. So if you think about telepresence, if I could get this transmission to you to be so good and so enveloping that you really thought I was in the room, then you wouldn't have to really think about going to a meeting and talking about things face to face. We could essentially observe nuance in each other and understand what we're trying to say directly through telepresence. So that pushes us to a metric of what is the function that we're going to get out of that telepresence per joule of energy invested, and then can we trade that off against the carbon footprint of travel and exposure to global pathogens that we're creating with our emissions, and the efficiency and security that we would get and in the systems and so forth. So if you just do a calculation of a rudimentary system, 7,680 pixels, 4,320 pixels, times 3 12-bit pixels at 240 frames per second, and just 2 cameras, that comes out to 600 gigabits per second per user. And then if you scale that up to what we think would be the equivalent of real presence with 256 views and 600 frames per second, that would be 180 terabits per second per participant. So clearly, that's not going to happen. But we have to think about how we're going to produce the transmission, how are we going to transport the transmission, what sort of processing is it going to encounter, and how are we going to display it. And I'll give you an example of the work that's going on for the 2020 Tokyo Olympics and talking about how this processing is going to happen. And some of this comes from a presentation given by Chris Chambers from BBC at the meeting that we had last week here at MIT. So the idea there is that, and this is a commitment by NHK for the Olympics. In 2020, the stadium will be covered by 8K ultra-high definition cameras. And the question is, well, how do you site those cameras around the stadium to give you the feeling of telepresence? And if you think about the uncompressed data, because you don't want to have too much in the way of latency, because that would really make things bad. Uncompressed data, you're already into the terabit per second, and just for that application. So the feeling is that in order to extract a live multi-platform scene from that stream, you have to, first of all, think of the system. How are you going to synchronize the cameras to one another? How closely should they be positioned? You're certainly going to need optical connections for that data. And how are you going to use that between cameras and in the scene processing? And for the scene processing, you really boil down to the question of how much reality do you have to transmit? Because you'll have a computer in the data center which is doing virtual reality simulation of as much as it can in order to require only small amounts of data that relate to changes in the scene. And so we end up with the term, which is quite intriguing, live virtual reality, in which we're trying to get the nuance of live, but we're dependent because of the data capacity to do a lot of simulation in order to transmit it. So that's a question of, well, we can think about how to get the data rates up as that high in order to get the raw data out of the camera, but what sort of processing do we need, and how are we going to keep density while we're doing all of this? Because remember, we're scaling with density. When you go to sound, it's another question altogether. Sound really doesn't represent a data challenge as far as data rate. You can get a stereo stream at 48K 24 bits in the 3 megahertz bandwidth. But sound is very nuanced as far as perception. So the super high vision, which is going to be implemented in the 2020 Olympics, is going to carry a 22.2 sound format, which requires 24 audio channels in layers. And those layers depend on frequency and so forth, and position and so forth. So the question is, we really don't need a lot of data, but we do need a lot of understanding of how that data transmits sound that can be interpreted by people with a number of different hearing characteristics and a number of different receivers on the other end, 7.1, 5.1 stereo, mono, and so forth. So capturing, transmitting, and reproducing audio perception is really an even more unsolved problem than the video. Now let's think about the last application, RF, 5G, and LiDAR. And as I said earlier, it looks like those are all converging on the same platform, even though the details are certainly going to be up for grabs. If you think about what 5G is aiming for, it's just simply everything, right? in the lower left-hand corner, it's going to do everything. In the right-hand corner, it's going to provide instant action. So latency's got to be squeezed out of the system. And in the top middle, it's going to be that experiential telepresence kind of thing that you need as well. So we can sort of portion out what the data capacity needs to be for these. If we think about conventional free space communication, whether it's RF or optical, we can look down the list at the table in the upper right and say, well, optical is good for directionality and low interference. The RF is good as far as the signal quality at this point. Because we don't have the need for filters in order to push out the light interference. But light is the best bet for getting high density as far as both your data rates as well as your hardware. So if you think about RF photonic communication, you'd like to combine the two. You can do that and get the advantages of actually being able to image different sources of RF signals on a detector plane. So then with each detector, you can do signal binning from the RF and get your channelizing. But you can also do source binning with the spatial selectivity of being able to do that imaging. So if you can do passive optical processing of RF signals up converted to an optical carrier from multiple sources, it enables both of those. You can passively do a fast Fourier transform channelizer, and you can passively do an optical lens that can re-image the sources onto individual photodetectors. So with this, you can envision that size, weight, and power go down as well as costs with integration. And I thank Dennis Prather for teaching me all of those things. With 5G, one thing that I learned is that 5G is going to be much more directional than current 3 and 4G, which are more broadcast. And the idea is to get the sensitivity and efficiency increase of directed beams. So when you think about that, without even trying to go into detail about how that's going to be accomplished and what we're going to get out of it, besides the efficient point-to-point communication, you can see that it is the beginning of optical matrix address technology. And we're going to think about having XY optical matrix address in order to do beamforming with phased arrays and do the same thing in reverse to be able to get a detection from spatially resolved sources. And the whole idea there is particularly strong when we think about sensors, where we're looking for patterns to give us an idea almost more often than we are amplitude as to what the source of a particular pathogen might be or where a leak is occurring and so forth. So lumping all of these things together onto a common platform, I think, is going to be something important in the future. Sensing, we just look at the big needs for sensing, and mainly people are thinking in terms of IoT and sensor integration. If you think about the basic sensor component, you need a photon source, which may even be ambient light. You need a filter, so you can be selective. You need a detector, and you need an ASIC to determine whatever signal you get. So the word that of caution there is you don't need to get terribly sophisticated. Free space apps should not be neglected, particularly when you're doing spatially resolved sensing, and that's your target. When you think about IoT and sensing, Internet of Things, both tethered and energy scavenged power is going to be important, as well as reliability and so forth. So we need to think about how we're going to be able to integrate those into the system, and that's where sensing and RF and so forth are going to be converging. One of the important things that's emerged in the past year is the ability to do both index and absorption sensing at the same time. And what this allows is the ability to do quantitative analysis of multi-component systems. So you can do a mixture and know exactly what the calibration scheme is for one concentration versus the other in that mixture. Another thing that is now universal is the ability to integrate optofluidics on chip. And so this allows you to condense the sources into small volumes as small as 0.1 microliter for analysis. And then lastly, using optical switches to create a digital Fourier transform spectrometer. It's a simple concept as far as switching is concerned because you don't need really high-speed switching. But essentially, Fourier transform spectrometer uses a Fabry-Perot cavity to sort out the different wavelengths depending on the resonance in that cavity. And you can create different size cavities with optical switches, implement them in silicon photonics, and it's been demonstrated to be very effective. Let's look at economics as we're winding down. One of the big issues driving disaggregation in data center systems is the fact that different parts of the data center have different trends as far as their cost and performance scaling are occurring. So if you want to upgrade a CPU or a memory in a traditional design, traditionally you would just have to put a whole new server with a new motherboard design at considerable expense and economic waste. And in driving the whole idea of disaggregation, Intel and Facebook came up with some very telling data as far as the savings that you would get to just refresh one component as much as 44% rather than trying to refresh the entire server blade or the entire data center, which was what was done up until very recently. Now, one of the things that when you dig a little bit deeper into that, is you realize that when a data center makes a decision as to when to upgrade, they not only think about how much the upgrade is going to be as far as the change in capacity, but they think about, do I need to write new software? Do I need to train new people? When is this going to come in? And how much is it going to cost? And am I going to be able to use all that capacity immediately or not? And it brings in the idea of a data center inventory cost. So typically, you buy the capacity ahead of time, and that capacity is ramped up slowly into the data center until you have your next up ramp in capacity. So the bandwidth versus time for the data center goes in steps. If you're running a data center, you think about that bandwidth that isn't being used as inventory. I've paid for it, and now it's incurring an inventory cost until I'm actually using it to generate revenue. So when I think about what my costs are going to be, they're going to be involving not only the ability to use that inventory, but also the cost to implement it. So when you think about the total cost, it's of course the purchase and operating cost, but it's also that inventory cost, and it is weighed against the shortage cost that if I don't have that capacity, I'm not generating the revenue that it would have presented. And when you put all that together in a cost model, you get something which is this green line, which is an ISO total cost curve. And it essentially tells you that I might want to stick with 100G because it's available now and I can upgrade in smaller increments. But if I go to 400G, I'm upgrading in bigger increments. I have a longer lead time as far as implementing it and getting into my system, and a longer lead time as far as when I'm going to utilize it because my inventory is going to be larger by using these larger chunks. So that goes into the decision, and what it's telling us is that when we construct the supply chain in order to support the data center, we need to think seriously about how we're going to be able to supply these very fine-grained upgrades rather than big solutions. So this is just an example for those of you who aren't already involved in the road mapping. So you look deep into the supply chain. This is just looking at an integrated waveguide roadmap and the need to generate more power per waveguide with system functions. And silicon waveguides have a limit of about 30 milliwatts if they're fully confined. So there's a need to go to higher power capacity with nitrides, and then eventually to multi-layers so that you can get dispersion control and things of this kind. And while you're doing that, what the industry is asking for, we need 3D waveguide capability in order to get more density, routable optical layers, and how are we going to do that, and how's that going to affect cost? So if we look at the foundry model that's going to be accommodating all of those things, now we have a foundry PDK, process design kit. You have a design manual, you have a process flow, and you have a device library with compact models that you can use to do design. But when you start to do manufacturing for your product, you want more than that. That's very good for doing the R&D in sort of the middle technology readiness levels. But when you go to manufacturing, it isn't just optimization of the nominal design. It's the ability to do, understand what the sources of variation are and how those are going to affect the variation in your design inputs and output, and then do design centering that will compensate for those and open up the tolerances so that the end result will be consistent with the desired performance. So that second part here is going to be the focus in 2019. This is a problem that is going to be solved in 2019 because it has to be solved both at the R&D foundry level as well as at the product foundry level. I just thought I would conclude with something that's going on in the automated design part, which is something that's being produced by AIM at the AIM Academy called the Virtual Design Lab. So AIM has summer schools and winter schools which are taught for photonic integrated circuit engineers, and is now starting a certification program in fab and test for technicians. But at the heart of that is to create some kind of intuition as far as how to do design, how to understand when you're doing testing or when you're working with a fab tool, what exactly is that variation doing as far as the process is concerned. So this slide gives an idea of looking at the simple example of a directional coupler and how that can be used at all levels of skill set. So basically, for a directional coupler, you want to know the length of the coupler, the gap spacing between the two waveguides, and what is the wavelength, and that'll determine the behavior of the system. So you can modify the length. If you look at the top, you can see the optical signal coming in and how it's coupled in and out of the waveguides at a particular length based on a fixed wavelength and fixed gap spacing. And you can do those changes for the gap spacing as well as the wavelength, and get an intuitive insight as to what is going on as far as that design is concerned, and at the same time understand when you're doing coupling for test or manufacturing, how these things are going to play into the thinking. And you don't need to know a tremendously deep part, but these are also being used for engineers that are currently working in the industry to as sort of a front end for understanding how to do automated design with commercial software. Okay, so I thought I would conclude with a few bullet points that came up at the recent meeting at MIT, which we sort of add into our area called lessons learned. So I have two slides, one on technology and one on applications. For data centers, there are 20 million square feet of data centers in the world today, and that's increasing at a rate of 2x every 2 years. So if there's a new Moore's law, it's how big is the data center going to be over the next 100 years, and it's going to take over the globe if we don't do something about it. So density looks like a pretty good scaling paradigm. The intra-data center short reach trade-off is very important. Are we going to stick with multi-mode, or are we going to go to single mode and solve the connector loss problem? If we look at fiber connect, how are we going to deal with the surface mount transceivers in the beginning and the pluggable fiber connector that doesn't really exist today? Chip package co-design, we need to be able to not only do a good transceiver and a good ASIC, but they interact through parasitics and so forth together. And once they're in the same package together, we need to be able to do a co-design of what that performance is going to be. And that needs to be pushed all the way back to mid-TRL levels when we're doing our chip design. System and package, how are we going to get edge fiber connects capable of doing 128 fibers per chip edge? Interposers, active, passive, digital RF, and so forth. The interposer is going to be the key solution to packaging in the near term, and it will probably be the key PIC evaluation platform as well. So we need to be able to do that at low cost and very high throughput in order to go through design cycles as well as make product. Lasers, where are the lasers going to be? We know what the reliability characteristics are for lasers that are created independently. A MACOM laser, 95 degrees centigrade, no change over 1,000 hours is their criterion. But we need to think about, can all of these things hold up when we move the laser into the package or we move it into the data center rack? Design for manufacturing, I mentioned earlier, statistical models, nominal design optimization versus design centering. AIM is just introduced as PDK 2.5, which has an advanced process flow with compact models and a very high performance device library. If you look very far into the future at that quantum option for enhancing system performance, we're beginning to see actually functional modules being created. Quantum entanglement, which is a way to enhance security over long distances. Now we have quantum entanglement repeaters that have been demonstrated. So for the technology scaling, it looks like density is number one. You can translate that into terabits per second per cubic centimeter or per cubic millimeter, if you like, or you can translate that into joules per function, if you like, as we discussed for telepresence. For applications, the markets are increasing as well as the support for that. It's being driven by the fact that the average age of the world is increasing, the average education is increasing, so people are actually expecting more technology to be incorporated into their lives. The semiconductor industry itself, traditionally for electronics, $350 to $450 billion. So photonics has to penetrate into that. So the 3 to 6% scaling in different market sectors of that industry can be translated into much larger scaling with good enough photonic performance support of that. Data centers we discussed, RF for 5G we discussed. Sensor systems, the only caveat there is if you have something that actually has a response to the outside world, then people will ask you to deploy that for their application. We heard at the recent meeting, Analog Devices sensor platform, they're looking for that to be as big as their MEMS platform, which is a pretty good, pretty optimistic look into the future. And lastly, 3D time of flight for facial recognitions, for sensors in general, and then for microscopes and surface roughness measurements and things of that kind is going to really have a fast ramp, and we're already beginning to see the supply chain coming into play. So thanks to everyone. We have a few minutes for questions. My acknowledgments to everyone below who's contributed through the road mapping. We have the next roadmap meeting will be in Tokyo in January of 2019. The one after that will be in Sunnyvale in March of 2019, and the one after that will be in June in Berlin in 2019. And it's a very rich group of people creating a very important knowledge base for creating a supply chain that can serve the industry. Are there questions?
Yes, Professor, there is a question from Paul Fortier from IBM, and I will unmute him now. Paul, are you there?
Yes, I am. Am I unmuted?
You are unmuted.
Okay, great. No, we had a question because we know with all these board level connections between doing an LGA socket solution or a reflowed solution, we're just wondering the work that is going on with this expanded beam connectors, whether right now one of the current goals is to have those solder reflow compatible.
Yes, it is. Actually, I went into some detail in that in my report last year. I think, if I recall, the temperature for reflows around 260 C. You probably know it better than I do.
Yes.
I think that's right. And so essentially, the limitation is if you have molded plastic parts, are they going to survive that reflow step? And that's where the I guess the tires are hitting the road, and that's exactly what this group is looking at.
Okay.
If you're interested in details of that, I'll connect you with Terry Smith at 3M, who's leading that particular part.
Okay, so the solution is not there yet. But it's part of the objectives.
It's definitely very high on the list, right?
Okay. Okay. No, thank you.
That is all the questions I'm showing for the moment, Professor.
Okay. All right. Well, thanks everyone. We've utilized our time plus a few minutes, and I wish you all happy holidays, and welcome you to join any of the technology working groups or any part of this that you think it would be beneficial to your own efforts. And it certainly has been an eventful year for all of us, and we're looking forward to even more eventful next year. Happy holidays.